What you're looking at right now is a dipole model of the Earth's magnetic field. Or rather, you're looking at a slice of it in the XZ plane. This is what it looks like in 3 dimensions. We know that the Earth has a magnetic field. It's what protects our planet from cosmic radiation and solar winds, both of which can be harmful to life on Earth. But how exactly does it do that? To find out, we need to better understand a portion of the Earth's magnetosphere, namely the Van Allen radiation belts. These belts were first discovered in 1958 by James Van Allen, an American astrophysicist from the University of Iowa, who stumbled upon the phenomenon while searching for cosmic rays. With the belts being mainly composed of high-energy particles, it was quickly inferred that this radiation could pose a challenge to manned spaceflight. In fact, the risks associated with traveling through them were initially thought to be quite severe, due to a lack of general knowledge about the actual radiation levels. But after further research, we realized that this fear was for the most part unrealistic, since the relative radiation levels from exposure to the belts are not substantially higher than those from other more common sources, leading us to conclude that only long-term exposure will cause significant effects.
Fortunately, since their discovery, the research conducted by NASA in the 20th century has allowed us to gain a slightly better understanding of the behavior of charged particles in the Van Allen belts and how they get trapped there in the first place. These belts aren't particularly visible, of course, but they roughly follow Earth's magnetic field lines, stretching along elliptical curves between its magnetic poles with near-complete rotational symmetry about the axis of its magnetic moment. The charged particles that make up each of these belts are primarily protons and electrons. It is commonly believed that most particles trapped in the belts originate from solar wind and cosmic rays. The outer Van Allen belt consists mainly of electrons, which likely originate from solar winds, whereas the inner belt consists mainly of protons produced from the decay of neutral particles in response to cosmic ray collisions in the upper atmosphere. These particles interact with Earth's magnetosphere and as a result exhibit some particularly interesting behaviors. In fact, there are 3 key effects that can be observed from these magnetic fields interactions. They are referred to as gyration, bouncing, and drift, which we'll cover in more depth later. While in class, gyration was mainly discussed in terms of uniform magnetic and electric fields, here it becomes relevant without the need for an electric field due to the non-uniformity and curvature of the magnetic field. To see these effects, we simulate the trajectory of particles trapped in the Van Allen belts.
We can derive the equations of motion of charged particles in the radiation belts using Newton's second law. We have seen in class that the complete description of electromagnetism is given by the Lorentz force. For the following derivations and demonstrations, we assume that the electric field is negligible. We can make this approximation because the magnetic field dominates over the electric field in the regions occupied by the radiation belts to quite a few orders of magnitude. Our net force then simply reduces to the magnetic force. Due to the complex nature of Earth's magnetosphere, we may model the magnetic field to first approximation as a dipole field, aligning our dipole axis with our z-axis. The magnetic dipole field of Earth in spherical coordinates is shown on screen. To perform numerical integration, we found it simpler to transform the magnetic field into Cartesian coordinates. You may pause the video if you wish to take the time to follow all the steps yourself. Combining the magnetic force with Newton's second law, we can write the following equation. However, particles frequently attain relativistic speeds inside the belts, and thus special relativity should be considered. Using relativistic momentum, we obtain the following equation. Furthermore, because of the cross product, most of the particle's velocity will be angular. The speed of the particle and consequently the Lorentz factor will then remain relatively constant. We then obtain this acceleration vector. The resulting equations of motion in the respective x, y, and z coordinates are shown on screen.
We then applied the numerical differential equation solver method, Runge-Kutta-4, with inspiration from this research paper, in order to demonstrate the motion of charged particles in the Van Allen belts and their relevant entrapment and deflection behaviors through some customized animation of the particles' trajectories. Essentially, all these instances are an illustration of the complex interactions between the Earth's magnetic field and moving charged particles in its vicinity, where we have used numerical integration techniques to solve a set of highly coupled differential equations describing a particle's movement. We will continue to show you some simulations as we further analyze each component of the underlying physics. The gyration radii of the particles trapped in the belts are related to the ratio between their mass and charge as seen in class, according to the following derived expression. The gyration frequency can also be derived in a similar manner. In addition, as we move away from the Earth, the radiation belts get much wider as the weaker magnetic field leads to a larger gyration radius of the particles trapped within it. It is worth mentioning that negatively and positively charged particles also drift in different directions. As we mentioned previously, the belts stretch between the magnetic poles of the Earth, but you may rightfully wonder why this is the case. In fact, this occurs precisely because of the strong magnetic fields near the poles, which we can see increase as we approach them roughly parallel to the magnetic field direction itself for small enough distances away. With this magnetic field magnitude gradient essentially parallel to the magnetic field, the particles are slowed down and eventually bounce away from the poles, causing the particles trapped in Van Allen belts to continuously oscillate between the Earth's polar regions without ever hitting the surface. In addition to the helicoidal and bouncing motion along the magnetic field lines, charged particles also drift perpendicularly to the magnetic field lines due to the gradient that arises from the curvature of the field. Although drift motion is much slower than gyration or bounce, it can be appreciably observed further away from the Earth on larger timescales.
More complex particle behavior also arises when we model the Earth's magnetosphere with greater accuracy, accounting for more of its subtleties such as the time dependence of its magnetic field. Many of these phenomena are not particularly well understood. For example, the changing structure of the radiation belts during geomagnetic storms is still under study, with no current consensus. During solar winds or coronal mass ejections from the Sun, magnetic material can collide with the Earth's magnetic field and as a result cause a temporary change in electron density in the belts. In fact, this can in some cases lead the electron belt to temporarily separate into 3 distinct bands for short periods of time, or even cause the gap between the inner and outer belts to briefly disappear entirely as shown in this figure. Similarly, outer belt electrons with ultra-relativistic energies seem to be blocked by some barrier at the inner radius of the outer belt, causing the separation we see between the two belts. There is still no agreed upon theory for this behavior, especially since the research has shown that the Earth's intrinsic magnetic field and other electromagnetic fields, such as human-generated transmission, cannot cause such a barrier. Since their discovery, the study of the Van Allen belts over the years has impacted various fields of research. For instance, work has been done on meteorological models with the National Oceanic and Atmospheric Administration to relate the low-energy electrons falling out of the belts to what are known as chorus waves, a series of electromagnetic waves which can cause northern lights in the atmosphere. Currently, plasma physics is also being used to theorize how the Earth's plasmasphere could explain the gap in between the two belts. There are so many things left unexplained about the belts which we simply do not have time to cover today, such as the South Atlantic anomaly, in which a portion of the belt inexplicably gets very close to the Earth's surface and affects satellite electronics.
Overall, we hope to have helped you see here today the interesting characteristics of the Van Allen belts. We've mentioned throughout this video how the deflection and entrapment of high-energy charged particles occur, and we hope that this has helped you to gain a better understanding and appreciation of the work done by our lovely magnetosphere to make the Earth a relatively safe and habitable place for humans, protecting us from what otherwise could be a veritable deluge of solar radiation.